We have learnt about Onsager reciprocal relations in our previous lecture, and now today we are going to see how these relations can be proved. So this is the today's lecture is the subject matter of proof of Onsager reciprocal relations. So first of all, you have to think how we can proceed to prove these relations. In other words, you can say what will be our plan. Actually, for the proof of these relations, we shall utilize the statistical mechanical theory of fluctuations together with the microscopic reversibility. On the basis of these two theories, we can easily obtain Onsager reciprocal relations. But for this, we have to take some assumption. So what will be our assumption for proving these Onsager reciprocal relations? In fact, for this we assume that the rate of macroscopic irreversible process is the same as the average rate of regression of statistical fluctuations in the state of the system. This will be our assumption. Okay. Now, how we can proceed? What will be our procedure for obtaining these relations? Actually, in two steps or in two processes, following two processes, you can obtain these relations. First of all, we will see fluctuations in an isolated system. When you say isolated system, that means a system which is isolated from its surrounding. There is no exchange of energy or any type of exchange, energy, mass, etc. With the surrounding. Then the system is called isolated. And for this, we consider there is an isolated system, and this system has been left isolated for a sufficiently long time so that the system acquires its equilibrium state. Okay. Now, the state of a system is always represented by a number of parameters, and those parameters may be local pressure, temperature, volume, density, entropy, etc. So in general, let us consider that the isolated system which we have considered, its state is represented by the parameters denoted by the symbol A1, A2, so on An. So there are a number of state parameters or state variables which determine the state of our system. And as I have told you that these A1, A2, so on An may be pressure, may be temperature, may be volume, may be density, etc. Okay. But as our system will be not in equilibrium state permanently, in that condition there will be a continuous change in these parameters. Okay. So there is a continuous variations or change in these parameters. And when a parameter deviates from its equilibrium value, the difference between the parameter at a particular time and its equilibrium value is known as a state variable. So if we consider an ith state of our system, and in that ith state, the state parameter is AI, okay, and its equilibrium value is AI naught. Then AI minus AI naught, that is denoted by the symbol alpha I, and you have learnt in my previous video that these alpha I are known as state variables. Okay. Now, as we have left our isolated system for a long time, so this system has achieved actually the equilibrium state. And you know, when a system is in equilibrium state, then in accordance with our elementary thermodynamics, the entropy of the system will have maximum value. And if the entropy will be maximum, then these state variables alpha I will be equal to 0. Okay? So you can say, as our system is in equilibrium, so its entropy is maximum and the state variables alpha I are 0. And that's why you can say the deviation of entropy, which I have denoted by the symbol delta S, from its equilibrium value due to the fluctuation alpha I will be given by a quadratic equation, and that is given as delta S equal to minus summation I greater than k from 1 to n del 2 delta S by del alpha I del k, and this 0 actually denotes the equilibrium state alpha I times alpha k. Okay. This quadratic relation actually defines the deviation of entropy of our system, which is denoted by the symbol delta S, from its equilibrium value. Okay. Now, if we assume a quantity denoted by the symbol GIK, defined by del 2S by del alpha I del alpha k, then this relation can be written as delta S equal to summation over I greater than k equal to 1 to n GIK times alpha I times alpha k. Okay. In fact, this GIK, this is, you can see, this is a mixed second order derivative, and this actually appears in Taylor series, and it is symmetric. When you say that it is symmetric, it means GIK is equal to GKI. And in other words, you can say that del 2 delta S by del alpha I del k will be equal to del 2 delta S by del alpha k del alpha I. Okay. Now, you have learned in my previous video that the generalized forces xi are given by the partial derivative of this deviation of entropy with respect to the state variables alpha I. So xi is given by del delta S by del alpha I. Now, if you will substitute the value of delta S from equation 1 and differentiate it partially with respect to alpha I, you can see then this del alpha I by del alpha I will be 1, and the remaining factor will be simply minus summation k 1 to n GIK alpha k. Okay. And if you want to find the time derivative of this deviation of entropy or rate of change of entropy, then you have to take the time derivative. This dot symbol, you know, denotes the time derivative, and that will be equal to what? For this, we will differentiate this equation 1 both sides with respect to time t, and the time derivative of this alpha I will be alpha I dot. Okay. So this result is delta S dot equal to minus summation over IK GIK alpha I dot times alpha k. Okay. But you know that this alpha I dot, you have also learnt in my previous video, that this alpha I dot, which is the time derivative of the state variable, that is simply the measure of generalized force. Okay. This is the measure of generalized force, and therefore this is equal to Ji, and the product of this GIK and alpha k, you can see here equation number 2, that is equal to xi, which is, sorry, this gi is not generalized force, but this is the flux, and xi is the generalized force. So this delta s dot is simply equal to summation over I ji times xi. Okay, actually with this negative sign implies that the entropy is decreasing, because in equilibrium state its value is maximum, and whenever the state will change, entropy will decrease. That's why here there is minus sign. Okay, and this is actually a very important result, and this will be used in our further calculation. You can see I have mentioned here that this gi, which represents the flux, that is the time derivative of the state variable alpha I. Now actually for getting the average or mean value of this product, we will utilize the Einstein's theory of fluctuation. And you know, according to Einstein's fluctuation theory, the probability P of fluctuations d alpha I is proportional to the exponential of the corresponding entropy deviation delta S divided by K, where K is Boltzmann constant. Okay. So if your aim is to find the probability of a state in which the value of alpha I lies between alpha I and alpha I plus d alpha I, what will be the probability of that very state? If that probability is given by P d alpha 1, d alpha 2, d alpha n, then according to Einstein's fluctuation theory, this will be actually equal to exponential delta S by K times this much. Okay. And therefore you can see from this equation 4 that e to the power delta S by K will be simply equal to the probability P, and therefore delta S by K will be equal to log P, and delta S will be equal to K times log P. Okay, K times log. This is actually the Boltzmann relation. You can say you have studied earlier in statistical mechanics that change in entropy is equal to K times logarithmic value of thermodynamic probability. This is same. Okay. Now after getting this expression for the deviation of entropy, we can easily find the average value of the quantity alpha I times xj, and this average value will be given by this relation. If you will multiply this quantity alpha I times xj with the probability of the state and integrate for all values of alpha, then you will get its average value. Okay, so this actually angular bracket represents the average value. Okay, now you know the generalized force xj is given by partial derivative of delta x with respect to alpha j, and you have seen that this delta s is equal to k log p. So instead of delta s, now you can write k log p. So this xj is equal to del alpha j k log p. Okay. Now let us substitute this value of xj, in equation number 6, and then you can write the average value of the product alpha I times xj is equal to k. K is a constant, so it has been taken outside of the integral. Alpha I xj, xj is k times this much. Okay, k has been written here, and the remaining factor del operated on log p by del alpha j. times this much. Okay. Now you can simplify this expression in this manner: k integral over d alpha 1 d alpha 2 d alpha j minus 1 d alpha j plus 1, and d alpha j has been written here. Okay. And d alpha n integral alpha I, which is present here, now we can write it here. Okay. And multiplied by partial derivative of ln p with respect to alpha j. Okay. So this is simply equal to k times this much. Okay. And here you can see p times partial derivative of log p by partial derivative of log p with respect to alpha j. This product can be written as del p by del alpha j. Okay. This is del p by del alpha j. So instead of p times del log p by del alpha j, I have written here del p by del alpha j. Okay. So this is the average value of the product alpha I and xj. Okay. Now we will integrate this part of the expression, that is the second factor, by the method of integration by parts. Here we will take this alpha I as the first factor or first function and del p by del alpha j as the second factor. So remembering the formula for integration by parts, you can easily obtain its value. Here the limits are from minus infinity to plus infinity for all space. That is integral over alpha I times del p by del alpha j d alpha j. What will be this? You know, according to the formula of integration by parts, this will be first function times integral of second function. What will be integral of this second function? Integral of del p by del alpha j d alpha j will be equal to simply p. Okay, because integral cancels the differential, and limits are minus infinity to plus infinity. Okay, and then we put here minus sign according to the formula, and then integral, then there will be the derivative of first function. Derivative of first function, that is derivative of alpha I. This will be del alpha I by del alpha j. Okay. And integral of second function. Integral of second function, that is del p by del alpha j d alpha j. This will be p. Okay. So this is the second term. Now you know, at the limits alpha I equal to plus minus infinity, that is both at plus infinity and minus infinity, the probability of finding the system will be 0. So this first term will vanish. Okay. And therefore only this second term will remain here. Again, you know that this del alpha I by del alpha j, what is this? According to the definition of Kronecker delta, you know this is simply the Kronecker delta delta ij. And you know delta ij is equal to 1 when I is equal to j, and it is 0 when I is not equal to j. Okay. So if you will substitute this value here, then the average value of this product xi and times xj, this will be what? See here, this is in fact minus k. Minus is due to this minus sign. You can say k integral this much, and p is at age, you can see here. And for this del alpha I by del alpha j, I have written this Kronecker delta, and d alpha j is also at age. Okay. But you know from the normalization condition that the total probability of finding of a system in whole space will be equal to 1. Okay. This is a common fact. And therefore this integral is equal to 1. Okay, and if it is equal to 1, then the average value of this product will be simply equal to minus k times delta ij. Okay, this is a very important result which we have obtained when we have considered the fluctuation of uh, in an isolated system. Okay. Now, as I have told you in the beginning of my lecture that we will also consider a principle of microscopic reversibility. So now we will utilize the principle of microscopic reversibility, and you know this principle actually implies the invariance of equation of motion of individual particles with respect to time reversal. It means the equation of motion of an individual particle does not change if we take minus t instead of t. If time is reversed, the equation of motion does not change, it remains unaltered. Okay? Now we consider the value of fluctuations of this alpha I at time t. Okay? And alpha j is the value of fluctuation after a time interval tau. And therefore we denote these quantities by alpha I t and alpha j t plus tau. Okay. Now the average of the product of quantities alpha I of t and alpha j of t plus tau after a long time will be what? This average can be defined like this. This inside this angular bracket we have written this product alpha I of t, alpha j of t plus tau. And this average will be defined by limit capital T tends to infinity 1 over t integral 0 to t this product. This is a common method for finding the average value. Here capital T is the total time interval. Okay. Now, from the general principle of statistical mechanics, the time average which we have defined in this equation 8, you can see for a single system is equal to average over a microcanonical ensemble obtained by using the probability function which we have defined in this equation number 4. In this equation 4. When you will define the average value of a microcanonical ensemble in terms of that probability function, the result will be same. Okay? And therefore, if we consider the average value of the product alpha I of t times alpha j of t, then it will differ from this average defined in equation 8 slightly. Okay? And that difference may be obtained simply by substituting t instead of t we can substitute minus t, and therefore we can express microscopic reversibility by this relation alpha I of t times alpha j of t plus tau, and that will be alpha j of t times alpha I of t plus tau. Okay. Now from this equation 9 we will subtract the same quantity this much. Okay. Average value of alpha I t times alpha j t, and after that we divide the expression by this time interval tau. So when you will subtract from both sides of equation 9 this quantity and divide the result by tau, what you will get? You can see we will get average value of alpha I times this much, and that will be equal to alpha j times this much. Okay, you can do the algebra. Now, in the limiting condition, when tau tends to 0, then you can see that when tau tends to 0, then this quantity will be what? When tau will tend to 0, in that condition, this will be simply alpha j minus alpha j at a time t plus tau minus alpha j at a time t. This will be just a change in alpha j, and when you will divide it by tau, you will get the rate of change of alpha j. So this quantity will be just d alpha j by dt, and therefore this is just time derivative. So LHS can be written as alpha I times alpha j dot, and similarly the RHS will be written as alpha j of t times alpha I dot. Okay, alpha. Now actually Onsager proposed a new hypothesis, and according to his new hypothesis, on the average decay or regression of a fluctuation follows the ordinary phenomenological macroscopic linear law of this form, which we have learnt in my first video on Onsager relation. This is given as Ji, which is flux, and this is time derivative of the state variable. Sorry, this is just okay. You can see. Okay, the page has been turned. Okay, alpha I dot, and that will be equal to summation over k Lik times xk. These Lik's are phenomenological coefficients. Okay. Now we will use this equation 11 in this equation 10. And after using equation 11 in 10, what will be your result? You can see, instead of this alpha j dot, on the basis of equation 11, you can write summation over k Ljk xk, and alpha I is attached. Okay. And similarly in RHS, instead of alpha I dot, on the basis of equation 11, you can write summation over k Lik times xk. Okay, and alpha j is attached. Now we have obtained earlier that the average value of alpha I xj you have obtained earlier, that this is equal to minus k delta ij. In equation A1 you have obtained. So instead of alpha I times xj, you can write this much. So alpha I times xk, this will be minus k delta ik on this basis. You can see. So I have written minus k summation over k delta ik times Ljk. Okay, and similarly RHS will be minus k times summation over k delta jk Lik. Okay. Now when you will in LHS, if you will take I equal to k, it means k will be replaced by I. Then this delta ik will be equal to 1, and k has been taken equal to I, so this will be then simply Lji. Minus k and minus k will cancel out. And in RHS, when you will take j equal to k, so here this k will be replaced by j, then this Kronecker delta will be 1. Okay, and therefore in RHS there will be only Lij. So you can see our result is Lji equal to Lij. And what are these? these are nothing but these are Onsager reciprocity relations, as you have learned in my previous video. Okay, so in this way we have proved the Onsager reciprocal relations, and I hope you have definitely understand it, because I am suffering from cold and cough. So I was very, feeling very easy in teaching you, and so I hope. Okay, thank you very much.